Hello everyone and welcome. This is the video for the Integration, Cointegration, and Stationarity lecture, part of the Quantopian lecture series. So we're going to get started just by going over to Learn and Support, clicking Learn. Then we're going to go to the lectures link right here. Click that and scroll down to Lecture 19. And we'll clone that right into our research environment with that link and get right into it. So what is the point of this lecture? What we're going to be covering here is some very basic statistical assumptions, starting with this idea of stationarity. And we're going to use that to talk about orders of integration and finally cointegration and how this all ties together in an algorithmic trading context. Now, what is stationarity? There are a few different definitions of stationarity, but what we're going to be working with is something called wide sense stationarity. And what that means is that the mean and variance, or standard deviation, I'm going to be using these interchangeably, are constant throughout the entire life of the time series. So if you look at any 2 points in time, no matter where you are, the mean and standard deviation are the same as they were before. So what this basically boils down to is that a stationary time series is all drawn from the same exact probability distribution, all with the same parameters. So in the case of it being drawn from the normal distribution, it has the same mean and variance no matter where it is. Now, why is this important? What it really comes down to is this is a fundamental assumption that underlies a lot of our statistical tests and a lot of our statistical models. For example, in autoregressive models, where we build a regression model of the future using terms of the time series in the past, or moving average models, where we build a forecast of the future using coefficients that are a moving average of values of the time series past. All of these techniques are based on this idea of stationarity. And what it comes down to is that you're fitting to a probability distribution. Whenever you build a model, you're fitting to some underlying characteristics of the data. And you want those characteristics to stay the same. You want your assumptions to continue to hold into the future. So if there is some sort of shift, some trend in the mean or standard deviation, or any of the other parameters of the probability distribution that your process is drawn from, then your model is going to have built on something entirely different from the current regime that you're in. It's based on entirely different assumptions, so there's no reason to believe that it's going to continue to hold. And that's why we need to know about stationarity and to test for this in time series analysis. So we just import some packages here and define this generate data point function, which is just going to draw a sample from the random normal distribution for a given mean and standard deviation. And we'll just be using this to generate time series. And then we have series A here. We're just going to generate a stationary time series from the normal distribution, parameters 0 and 1, and we'll just plot that so we can see what a stationary time series looks like. And we see, all right, we've got some white noise, right? That's exactly what this is. White noise is the quintessential stationary time series. It's oscillating all around the same point. It's staying within basically the same range. There's nothing weird going on here. This is fine. And this is just a sanity check, really, because we know that this is going to be stationary, because everything is drawn from the normal distribution. Now, what does a non-stationary time series look like? Well, as I said before, it's going to be anything that has a trend in the mean or standard deviation or other parameters of the underlying data. So if we generate that right here, we'll say that this mean now depends on t as we generate these 100 different samples. So the mean is going to be gradually increasing as we go. And we have that. And it looks right here. Like, this is very clearly non-stationary. It's a completely different beast from this guy up here. And this is just important to give you an idea of what isn't stationary. Now, why do we care so much of stationarity besides the assumptions and stuff? Like, even getting away from the models and statistical tests and everything, some of our most fundamental statistical techniques are useless for us when we don't have stationarity. So if we plot this non-stationary time series again and try to take the mean, just a point estimate of the mean, indicated by this red line here, we see that this isn't going to be informative at all. Our typical descriptive statistics just don't mean anything. We're not going to be able to use this to look at the future, the past. We're only going to be able to look at it exactly in this middle period here, and it doesn't really make sense to look at something that isolated when we want a mean of the entire time series. That's the extra information that we're trying to glean. We could do something like a moving average, where we have a moving window across the entire length of the time series. So we'd take the mean of stuff here and gradually just calculate the mean. And it'll smooth out this curve a little bit. But this introduces like a period of lag equal to essentially how long your moving average window is. So we're going to be getting the information that we want a lot later than we actually want it, compared to if we had just taken a point estimate. And this is one of the major disadvantages of non-stationary time series. Now, how do we actually figure out whether a time series is stationary or not? Luckily, we do have statistical hypothesis tests designed to check for stationarity. And we're just going to make use of that, of one of the most popular ones here, the augmented Dickey-Fuller test, and just define this check for stationarity function and use it to test whether A and B are stationary. So we'll run these two cells, and we see, okay, A is likely stationary, and B is likely non-stationary. That makes total sense given the definitions, just a sanity check, confirming it. The thing is, with a statistical hypothesis test, we do have a risk of false positives or false negatives. That's what is signified by this cutoff here. We have a 1% chance of getting a false positive. So let's try something with a more subtle trend in the mean. Like, this is so obvious that this is going up. Let's add some deterministic function like sine, which we know is going to oscillate between 0 and 1. So this is bounded, it's deterministic, but it's a trend that we might not be able to pick up with this statistical test. So let's see if we can get that. Looking at it, well, it looks a lot like the white noise process from before. It's just going up and down, it's oscillating all around the same area. But we know by definition that this is a non-stationary time series, that there's a trend. This kind of illustrates why it's dangerous to just look at graphs to tell you whether you're right or not. Ideally, we should be looking at graphs to tell us whether we are wrong, whether there is something that is obviously not characteristic of a stationary time series. Looking at this, we would probably say it was stationary, but we know it isn't. Unfortunately, or fortunately, I guess, our statistical test, well, it fails in this case. We know that it isn't stationary, but this test is telling us that it is stationary. So this just kind of illustrates the limitations of these tests. The ideal thing to do would be to try a few more tests, given we have the advantage of knowing that this is non-stationary, and if we were working with real data, we would likely just end up moving forward with it regardless. But it's difficult to pick up on these kinds of things. Not knowing otherwise, we would proceed forward, and that's totally fine. More often than not, this statistical hypothesis test is going to give you the right answer. So it's okay to place some faith in it, especially when we don't really understand the underlying relationship, especially if it's something more subtle like this. So let's have a look at an integrated of order 0 time series. We have A from before, which was stationary, and if we plot that here, well, we know it's integrated of order 0 because it's stationary, so here's an integrated of order 0 time series. If we want to build the time series that's integrated of order 1, what we do is we cumulatively sum an integrated of order 0 time series, our A. Basically a poor man's integration, which is where the name orders of integration comes from. So if we do that here and plot it, call it A1, we see that we're getting a little bit smoother. This is starting to look a lot more like a price process, which we can kind of see how these financial time series tie into this idea. If we want something that's integrated of order 2, well, we just take an integrated of order 1 time series and cumulatively sum that. And we'll call that A2 right here. And we see we're getting smoother and smoother and smoother. We can continue in this fashion until we get a time series that's integrated of order n, just by cumulatively summing an integrated of order 0 time series n times. Now to go in the other direction, what we need to do is we take the first order differences. So first, we're going to introduce a little bit of mathematical notation, namely this backshift operator, L. So if L is applied to any element of a time series, it immediately outputs the previous element of that time series. So here we see L applied to xt yields xt minus 1. So we can represent the first order differences, xt minus 1, as 1 minus L times xt. Now, this isn't super important. It's some somewhat obtuse mathematical notation. What's really important to take away from this is this notion of first order differencing. So if we have an integrated of order n time series and we take the first order differences n times, then we're going to be left with a series that's integrated of order 0. So let's try this out on some real-life data. Let's pull some Microsoft stock from 2014 to 2015 using like our built-in Quantopian functions. So we'll run that here, and let's check it for stationarity. If you've ever seen a price process before, we know that it's not going to be stationary just by looking at it. And we can plot that right here, and we see, obviously, this is a non-stationary time series. But let's take the first order differences. This looks a little bit like an integrated of order 1 time series. If we take the first order differences, maybe we'll be left with a stationary time series at the end of it. So we'll use the pandas functions here to difference this time series, first order, and we'll just check for stationarity using our function from before. And we see that these returns are indeed stationary, these additive returns. As a sanity check, let's also do the multiplicative returns using the percent change. So if we do that here, we see that these are also likely stationary. And these look, again, like white noise. Now, something to be concerned about when looking at real-life data is that if we've tested and determined that at some point in the past, the return series was stationary, or that the price series was integrated of order 1, that's not necessarily going to be true for the future. This is why we need to constantly be checking whether our base assumptions hold when we build a model, because things can shift, especially when we're not really expecting them to. Now, generally, we assume that return streams are going to be stationary. And this is just a base assumption of a lot of financial mathematics, because it's rooted in the idea that prices are log normally distributed. Therefore, the price series, the return series is going to be stationary, or normally distributed as a result. Now that we've covered stationarity and orders of integration, we can finally get into cointegration. But first, we have to define what a linear combination is. So if we have some set of time series, x1, x2, x3, x4, and so on and so forth here, y is linear. So if we have some set of time series, x1, x2, and so on and so forth up to xk, we can construct a linear combination of these separate time series by adding them up and multiplying them by a variety of different constants. For example, if we have y equals 5 times x1 plus 2 times x2, then y is a linear combination of x1 and x2. It can be as long, we can use all k time series as here in the theory, or we can use smaller examples, just like x1, x2, only a few time series. Now, if we want to have a co-integrated set of time series, we need a set of integrated of order 1 time series, x1 through xk. And if there is some linear combination of all these x's such that the linear combination is integrated of order 0, then that set of time series is co-integrated. So if x1, x2, and x3 are all integrated of order 1, and this linear combination is integrated of order 0, then these time series are co-integrated. So co-integration is a useful idea because when we're dealing with real-life data or any data in general, and we're trying to build a model on it, we don't have a lot of information to go on. Our statistical techniques can tease out a little bit of the meaning, but there's only so much we can go on. Like, if we have a stationary time series, that's all we really know besides like its parameters, and we can test to figure out what sort of distribution that it's drawn from. However, if we have a set of co-integrated time series, this indicates that there is some sort of subtle relationship between the time series that are involved. So if x1 and x2 are co-integrated, then there is some driving underfactor between x1 and x2 that could clue us into like this greater relationship between them. It gives us one more bit of data to go on. So let's just simulate what a co-integrated set of time series looks like. So if we have 100 samples of this random normal distribution, we'll cumulatively sum it here, call it x1. That's going to be an integrated of order 1 time series. That'll be our x1. And we'll say that x2 is equal to x1 plus some additional random noise. We plot them here, and we see, all right, it looks like they're moving together. This makes sense. x2 basically looks like x1 with a little bit of noise on top. Now, we know that x1 is integrated of order 1 by definition because we took a stationary time series and we cumulatively summed it to get it. But let's just double check to make sure that x2 is integrated of order 1. So we'll take the first order differences here, and we'll check the result for stationarity. So if we do that, we see that z, the differences of x2, is likely stationary. Awesome. So by construction, we already kind of know what this linear combination is going to be. So we just say that z is equal to x2 minus x1. We'll plot that and check for its stationarity here. And we see, all right, z is likely stationary. That means that x1 and x2 are co-integrated. Fantastic. Now again, real-life data isn't going to be as nice as simulated data. We're not going to know specifically what the linear combination is between the things we're trying to test. So in order to do this, we need to figure out some tool that we can use to figure out the coefficients of a linear combination. So in this case, what we're going to use is linear regression. It's a simple, quick and dirty way to try to get this beta out that we can then use as part of the linear combination. So let's pull some financial data, ABGB and FSLR from 2014 to 2015, right here. And then let's plot it here. And we see that, all right, it looks like they could be moving together. We're not really sure. Like FSLR seems like it's moving around a lot more than ABGB is. So let's calculate the linear regression between these and see if the beta will allow us to construct the linear combination that's integrated of order 0. So we'll use a stats model as a Python package here to just do a simple ordinary least squares regression, and we'll pull out what beta is. And we get that beta in this case is 1.536, so 1.54 about. And we'll define z, our linear combination, as x2 minus b times x1, check for stationarity, and plot z. And we see that, all right, z is likely stationary. Awesome. If we plot z, it looks like it's a little funky here, but the test is telling us it's stationary, and we're relatively confident in the test. So we can conclude that during this period of 2014 to 2015, the FBGB and FSLR, or ABGB and FSLR, are co-integrated. Now again, similar to the issue with stationarity, this is only a forecast. We can't be sure that two stocks that are co-integrated in the past are going to continue to be co-integrated in the future, especially since we have more things going on. We have an entire other relationship to consider. Generally, when we're looking for co-integrated stocks, we're going to be looking within some universe where we think that there's already going to be an underlying relationship. So we'll look at stocks within the same industry, or we'll look at stocks in closely related industries. Like we'll see if individual shipping companies are co-integrated, or if a manufacturer and a supplier of steel are co-integrated, that kind of thing. But if there's some sort of regime change, if one of these companies gets a completely new management, decides to start switching what they're doing, then a pair that was previously co-integrated may become non-co-integrated in the future. We'll just get a lot of nonsense. So if we try to make any bets based on co-integration, well, we may run into issues. Now, co-integration is the core idea behind pairs trading, which we cover in another one of the lectures as part of the lecture series. And pairs trading is basically based on this idea that of co-integration, where if we have some linear combination of the stocks, it's integrated of order 0, so it's going to follow some probability distribution. So we can bet on this spread between stocks based on the linear combination and use that to inform our stock purchases. Now, in the real world, we don't necessarily have to deal with this whole process of constructing a linear regression and then making a linear combination and testing to see if that's stationary. We do have built-in tests of co-integration, and they basically amount to that. But in the stats models package, again, we have this coint function, and that'll tell us whether x1 and x2 are co-integrated. Here's the p-value, and we can conclude that yes, they are co-integrated from this test. So if we want to basically apply the co-integration test to more different independent pairs of stocks, then we can use the co-integration function instead and make our lives easier.
Hey everybody, thanks for watching the Quantopian lecture series. I just wanted to let you know you could get more content if you are interested. Here's the Quantopian lecture series page. This is available at www.quantopian.com/lectures. It's easiest just to Google Quantopian lectures. And if you're already on the Quantopian website, you can get to it via Learn and Support, Learn Lectures. Every lecture has a notebook. Most lectures will have videos you can watch to follow along, just like the one you're watching right now. And in addition, some lectures also have sample algorithms you can clone and play around with and maybe even use to start developing some of your own trading strategies. In addition to the lecture series, we have GitHub, in case you're interested in checking that out. That's github.com/quantopian/research_public. And we also have my Twitter account @TheStreetQuant. Finally, we also have services for schools and academics, and that's quantopian.com/academia. You can see here some of the offers that we have for professors. Everything is free, but we offer a little bit more help to educators who want to use the platform. Finally, you can always email me at delaney@quantopian.com. Again, that's DELANEY@quantopian.com. Feel free to shoot me any questions. We really appreciate feedback on anything we're doing here. Thanks very much.